All right, so good after lunch, everyone. Thank you for joining me for this talk. You know how is this talk called in speaker circles? It's called the graveyard shift. Right after lunch, people are completely gone. I actually say whatever I want, nobody would actually care. But I'll try to say things that someone would perhaps care. So welcome. This is a talk about writing a Windows kernel driver in 1 hour or so. So we'll see if we can actually get that done. It's not really going to be easy, and I'm going to move pretty quickly, so you actually have to be sharp, which is non-trivial after lunch. So anyway, my name is Pavel. I've been around the tech industry for a while now. I've written a few books. Please buy them. They make me money. And one of them is Windows kernel programming. So if you want to dig deeper into kernel development, that's one good resource to use. I've created a company called TrainSec, which is about providing training for security, cybersecurity, and low-level programming. There's lots of recorded courses there and some free stuff as well. The YouTube channel actually has many videos related to Windows internals and some C++, some other weird things that are mostly free, so feel free to check that out. I've also contributed to the sysinternals tools for those that know what these tools are. And I think that's enough because we just have 1 hour, in fact, less than an hour. So the plan is to try to build a driver and the client application that talks to the driver to do something which is useful. I mean, it's not going to be a crazy big driver, but it's going to be something that is at least useful in some way. So here's the plan. We'll talk about the basics we need to know. We'll talk about how we communicate with the driver, and then we'll start to write our client application with some additions related to the driver and the driver itself. And we'll see how far we can go. So here's what we're going to do in terms of what we want to achieve. So here's an example of some virtual machine. When you test drivers, you always test them in a virtual machine because drivers can cause your system to crash with that blue screen of death, or now it's black screen of death. If you have the Windows Insider preview, it's a green screen of death. So whatever screen that is, your system is crashing, so you don't want to test on your current system. You want to test on a different machine. And so that's one reason. The second reason that for debugging purposes, unless you're writing drivers perfectly the first time, you probably want to debug, so you need a different machine for kernel debugging. So what I want to do here is to have an application called list DLLs. Its purpose is to list the DLLs in a particular process. I have here Task Manager shown with some of the processes in that virtual machine. So I'm going to grab one of the Explorer processes as an example. Here's 2236 is the process ID, and I get the list of DLLs. Fantastic, I'll show you the code, not a very big deal. So let's suppose I want now to try something else, maybe one of these CSRSS processes here, like 1016, let's take one of them. And you notice I get an error, and the error is error number 5. Who knows what error number 5 is? If you've been in the Windows ecosystem, you should know that. If you're not, then that's fine. There are no penalties for wrong answers or for no answers. Yep. Access denied, that is correct. So this access denied thing means I don't have enough power to get the ability to see inside that process to look at its list of DLLs loaded there. So maybe I need more power. Well, I definitely need more power. So here's another command window I have here, which is running with administrator privileges. So maybe if I'm an administrator, I can get that done. So again, let's take one of these CSRSS processes, and I try this, and again, error number 5. Does anybody know why I can't do that? Why isn't that working? Yep. That's right. That's right. If you kill CSRSS, you get the blue screen. Well, that's actually not the reason, but you actually were very close in your in the first comment. So CSRSS is one of those called critical process. If you kill it in some way, it doesn't matter how, Windows crashes. But the similarity there is that this is in fact a protected process. And a protected process in Windows is a process you can't access invasively regardless of your credentials. You can be administrator, you can be system, you can be God. You can't do that. Well, maybe God can, but you can't kill something like CSRSS without a kernel component. So this is what we're going to do. We're going to create a driver running in kernel space to allow us to get a powerful handle to this process or processes like that. There are more than one, and we'll be able to list the DLLs there. So that's the idea. So right now, this is what the code looks like. This is the user mode code. What I'm doing here, this is C or C++, if you will. For those C++ aficionados, it's going to be a very simple thing. So I planned that so that even people that have no idea what C++ is, but can read kind of C or C# or something, they'll be able to understand what is happening here. So I'm getting in the command line the process ID. I'm going to convert that into a number using this str2ul or whatever function, and then I'm going to call open process. So open process is the function I need to call to get a powerful handle to access the process, because I need to pass this handle to list DLL. So list DLLs here requires a particular handle, and the thing is that the actual workhorse of this application is this function in num-process modules. Unfortunately, if you look at the documentation of this function, it requires a handle that has a certain power. And that power is exactly that. It requires the process VM read access and process query information. That's what I need. And unfortunately, for protected processes, you can't get that from user mode regardless of your blue eyes or system powers. So that's the problem. So we want to create a driver to fix that. All right, so I'm going to switch between slides and code. I'll try to code live. We'll see if that works for me, because this keyboard is a bit misbehaving, and we'll see. So what are drivers? Kernel drivers are just modules loaded into system space. You can think of them as executables or DLLs that are mapped into system space. They're running kernel mode, which means they have all the power of the kernel. But as the American like hero movies like to say, with great power comes great responsibility. So if you misuse that power, you get this blue screen of death that nobody likes. And so we have to be careful not to do things badly, because the kernel is unforgiving and immediately will just crash the system. We typically call the files with a sys file extension, but actually nobody cares about that. And how do you invoke a driver? How do you call a driver? The fundamental APIs from user mode are called read file, write file, device control. So once you have a handle to the object, you can to a file object, which actually represents your connection to a device that driver has created. You can then call read file, write file, or device control. And the names here are a bit misleading, especially read file and write file. It might seem that to mean read from a file or write to a file. This is not correct. In fact, it's read from a file object, write to a file object. A file object is an abstraction in Windows representing connection to a device that could be a file in the file system, but could be something else, like a virtual device or hardware device. It's similar to a file descriptor in Unix, Linux, if you are in those kinds of operating systems. And basically, what is a driver? It's a bunch of functions. We need to tell the kernel, here's the functions I support. For example, I may support read and write, but not device control. I may support plug and play, power. There are all sorts of callbacks or entry points I can support. I need to tell the kernel that so it knows to call me when it is appropriate. So here's an example of what that would look like from a call chain perspective. We have this little red line separating user mode from kernel mode. So from user mode, I'm going to call one of these three functions after I have a proper handle to the device. And that function is part of my application. And then one of these functions implemented inside kernel32.dll. Despite the name, it's a 64-bit and it is in user space, but that's a different story. Anyway, read file or write file or device control will call the appropriate system call. The system call is the mechanism to transfer control to the kernel, to ask the kernel to do something. This is how all operating systems practically work. So we're calling NT-read file or NT-write file or NT-device control file. This is an internal thing. We don't have to know about that specifically, and that's going to make the transition into kernel mode using one of the machine instructions, syscall for x64 and SVC for ARM. And that goes over that red line in some kind of quantum leap. Leap goes into something called the system service dispatcher. who takes a number which is passed there in a register, EAX, for example, in x86, and uses that as an index into a table known as the System Service Dispatch Table, or SSDT, that some of you probably know, and then calls the real function, like the real NT-read file, the real NT-write file, and so on. And that thing creates a data structure called the IR request packet, or IRP, which represents the request with all its parameters, like buffers, codes, whatever, and passes that to the appropriate driver. And that's the thing we want to write. And we get some kind of request, then we want to perform something based off of that request. So we're going to write this driver.sys. So in order to access, to get a handle to a device, we need to call a function which is called createFile from user mode. And again, the name is a bit misleading. It's not really creating anything like a file. CreateFile is short for createFileObject, which means creating an abstraction that can connect to a device, which could be a file in a file system, but in this case, in fact, it's going to be a device that our driver is exposing so we can connect to it. We can also do the same thing from kernel mode, but this is less interesting for the purpose of this talk. So CreateFile accepts a file name, but it's not really a file name. It's actually a bad way the documentation specifies for that parameter. It's actually called a device symbolic link. It's like a shortcut that can go to an actual file in a file system, but can also go to a different kind of device. So if you think about things like C:, we think that these are very fundamental. It's a very fundamental thing in Windows. It's not. It's actually a symbolic link. Just a shortcut to a device name. In fact, we have tools to show that. And so from the API perspective, the createFile function, if we give it a particular format, which looks like this, 2 backslashes, a dot, a backslash, and some name, this name is going to be interpreted as a symbolic link. And the driver on the other side exposes or creates that symbolic link to point to its own device object. This is necessary because createFile is somewhat limited in functionality. There are other ways to kind of go around that. So quickly, if you want to try this thing at home at some point, you can set this thing up very quickly. You can install Visual Studio 2022. Any edition works, including the community edition, which is free. You can install the latest Windows 11 SDK and WDK, the Windows driver kit. The name Windows 11 doesn't mean that you have to work on Windows 11. You can also work on Windows 10. That's perfectly fine. And you get, as part of that, a bunch of templates that you can use to start a new project, as we'll do right here. So 2026, by the way, for those that care about Visual Studio version, is supported already, but requires an insider preview, WDK version 28,000, if anybody cares, but it will be fully supported, I would guess, in the near future. In general, the kernel itself has its own API. It's a different API than user mode. When we work at trying to create a driver, we have to include some header files that are going to have the declarations for the kernel APIs. And the main header file is ntddk.h. That's the one. It's like the windows.h equivalent, so to speak, from the user mode side. And fortunately, if you're familiar with the Windows API, you might know that the Windows API is a one big jumbled mess. Naming convention is out the door, types are sometimes inconsistent. It's really, really a messy thing. However, the kernel is much better designed. The kernel API is very strict, it's very uniform, has these prefixes for functions to get a sense of which part of the kernel they're about. It's much more well organized, I would say. Granted, there are reasons why the user mode API is messy as it is, but we don't care about that here. So in general, when we look at kernel functions, most of them return something called an NT-status. This is just a 32-bit value where 0 means success and a negative value means some kind of error. So there's consistency. Almost all functions return this NT-status kind of thing. If that status then has to return to user mode using something like get last error, stuff like that, it's going to be converted to the appropriate relevant error as Win32 is the Windows API sees in user mode, where positive numbers in fact are errors and 0 is success. So it's not the same value, which is a bit annoying, but after like 10, 20 years, you get used to it. So what is a driver really? A driver is just a bunch of functions. we have the kernel, and the kernel calls a function. So first we have driver entry. Driver entry is the main of a driver. Every driver has a main function, and just like a normal application, it simply is called by default driver entry. This is where the thing we're going to start initializing our stuff. And then there we're going to tell the kernel about other things we might support, like the read operation, write operation, or some other operations. There's another callback called add device, which is irrelevant for our driver because it is used for drivers for hardware devices. We're going to write a driver for a software entity. There's no hardware there. So this particular callback has no meaning. We're not going to use it. And then we have dispatch routines. These are those particular operations I mentioned, like read, write, create, close, plug and play, power. There's 28 of those entries. It's an array of function pointers, and we'll fill out some of them, the things that we support. Anything we don't fill up is already filled in with a function that is called within the kernel saying unsupported operations, so we don't have to worry about that. There are other kinds of callbacks we might need for a real driver, especially when handling a hardware device, like an interrupt service routine, DPC, stuff like that, way beyond and not needed for our particular driver here. There are other callbacks that we can register with the kernel, like when a process gets created or destroyed. Things like that are very useful in cybersecurity space, and in some other kinds of drivers, but we don't need that for our drivers. So we don't have to worry about that because there's no way that can take an hour. It's going to take more than an hour. A few more details that it's worth knowing before we jump into code is that how strings are handled in the kernel. We know that the Windows API works in a very similar way to the classic C. A string is just a bunch of characters terminated with null. Windows works with UTF-16 strings, but other than that, it's the same idea, but the kernel actually works with strings in a different way. These are counted strings, and this is the structure used to manage strings. For most of the kernel APIs internally, this is how it works. So we have a pointer to a wide string, that is the UTF-16 string, and then we have the length, which means that this string doesn't have to be null terminated. It can be, but there's no such requirement. The confusing part is that the length and maximum length are in bytes, not in characters. So if you have a string with 10 characters, the length is actually 20 bytes. And you have to, of course, compute that correctly when you're building these kinds of things, and there are functions to help with that, like RTL init Unicode string, which we'll use as a simple demonstration how we initialize a Unicode string based on an existing null terminated string. So that's something worth knowing. And by the way, if you're looking at user mode with NTDLL, which is the thing that actually makes the transition to the kernel with all the system calls, it also uses these types. Okay. So now we can go back and start improving our code. So one thing that we have here, we're saying something like this on the user mode part. If we have a handle to a process, great. But if we don't, we have an error. So let's see if we can now insert the driver even before we actually write it. So we're going to say if there is no handle, which means the handle is null, so we couldn't open a handle to the process for whatever reason, probably because of that access denied kind of thing, maybe we should try with a driver. So how are we going to do that? Remember that to get a handle to a device, we need to call the function create file. So create file is create file object. And the point here is that this file name thing that is being asked from here is not really a file name. It's actually a symbolic link that has these two backslashes, a backslash, and a particular name. And I expect that name to be provided by the driver. The driver doesn't exist yet, so we can say whatever we want, and of course we have to match this thing on the other side. Let's call that a process power. The name doesn't really matter as long as it doesn't collide with existing names, but really it's on the driver side that has to worry about that. We're just like dumb clients who are saying, hey, if that's a device that exists, give me a handle to it. If I can get that, let's talk to it. So the next parameter is desired access. Going to be, I'm going to have a write access. Actually, I need both. So I have the generic read here, a generic write. So let's grab both of them. And then there's some desired, share mode, which we don't care about because it doesn't really matter for devices. There are security attributes we don't care about because we're not creating something new, so there's no way to set security anyway. And then we have a bunch of things we have to specify, and one of them is open existing, indicating we're opening a handle to an existing device. In fact, there's no way to create a new device. The other constants there are really just for actual files in the file system. Then there's some flags we don't care about, another parameter we don't care about, we just don't care about these things. So what happens next? If H device works, and the way I know that is if I get back something which is not invalid handle value. If it's not invalid handle value, which is just the value -1, this is what create file returns if it fails, then I know that I have a valid handle on my hands. If you're worried about that not equals kind of thing, this is still C, don't worry, C hasn't changed while you were sleeping or something. This is just I'm using a font that takes certain characters and puts them together in a nicer way. So it is the normal exclamation mark equal, so don't worry about that. It's not a brand new language you missed somehow on language feature, so it's all good. So once we have a handle in hand, we can call read file, write file, or device control. It's going to be based on how the driver was implemented. Since we're going to implement that as well, we can choose whatever we want. So what do you think? Who thinks read file is a good option? Raise your hand. Don't worry, no penalties for wrong answers. Who thinks write file is a good option? All right, we have 3 hands here. How about device control? Who thinks that is the good option? And some people just don't have an opinion. And that's also fine. Like I said, no penalty. So the idea here is that I want to give the driver a process ID and get back a handle, which means I require some input. The driver requires an input and also returns to me an output, which means that read file and write file can't be used because they're unidirectional. Either you read or you write. I need something that goes both ways, and that's device control, because device control, of course, if you're not familiar with that, there's no way to guess it, but device control has 2 buffers. So I can give an input buffer and get back an output buffer at the same time once the operation completes. So device control is the thing I want. So let's go ahead and call that. So device control requires the handle to the device first. So I got that. That's why I was working hard in the previous line. And then I need to provide something called a control code. A control code is some number representing my particular request. A driver can support many control codes. So we need to provide some control code. And for now, I'm going to say ioctl is just some define. Let's call that ioctl open process. And I expect the driver to define that for me as some number so I can use it. And since we don't have the other side yet, it's going to be squiggly for now. Then we have an input buffer. The input buffer is the process ID, so I'm going to go ahead and use %process ID PID to pass the buffer. The size of the input buffer is the size of PID. The output buffer should be a handle. So I should get a handle back here. So my handle right now for the process is null, is 0, so it's bad. If everything works as expected, it's going to be filled out with a good handle. That's my hope. The size of the output buffer in the same way is the size of H process, so the size of handle is just 8 bytes for 64-bit and 4 bytes for 32-bit. And then I need to also get the number of bytes that were actually written into the output buffer. This is necessary. The API forces me. I can't say that I'm not interested, so I'm going to just have to get it. And basically, we're done. I can, if I want to be nice, I can close the handle and all that. And I'm done from the user mode side. So if that works, the handle here is going to be valid, and I'm going to call list DLLs and hopefully see the DLLs. If it's not valid, then there's nothing really I can do, because the error could be different. For example, maybe the process ID is a garbage process ID. Maybe it doesn't exist. So it's not really about security or anything. I just can't get a handle to something that doesn't exist. Technically, I could have checked that here. I could have checked whether in open process the result is actually access denied. And if it's something else, then probably my driver is not going to be able to help because there's some fundamental problem like a bad PID. But to save some time, I'm not going to do that. Okay, so that's my user mode part. Now that is ready. I can build that, but of course it won't build because of that constant that we're still missing. So let's go ahead and start with the driver. I'm going to create a new project. I'm going to select an empty WDM driver template. Let's call that process power. It's a good name. I'm adding that to the same solution in Visual Studio. And this is an empty WDM driver. What is it? WDM is the Windows driver model. This is the fundamental model that Windows works with since Windows 2000. And that's what we need here for a more complex driver that uses hardware, requires to manage hardware device. I would use a different framework called KMDF, which is a wrapper on top of WDM. So it seems perhaps a bit pointless to have an empty project. In fact, it's not completely empty. There's actually a file here. This is an INF file, and INF files are used for installing drivers, and they are necessary for certain kinds of drivers, especially hardware devices. But our driver is not like that, so in fact, we don't need it. So I'm going to just remove it. It's just going to interfere mostly, so I'm going to delete that. Now, really, the project is empty. However, it has the correct settings for the compiler and the linker. That's the point here. I want the correct settings, so I don't have to worry about these things. Now I can just right-click and add a file here. Let's add a file like process power.cpp, and we can start working. So the first thing we need to do is add the header file that I mentioned, nddk.h. That's like the windows.h thing. Let me just zoom in a little bit. Hopefully it's good enough. And now we can write our driver entry function. I'll then summarize stuff with the slide. So driver entry, just like a normal main of an application, has a certain prototype. You can't just write whatever you want. And this is what that looks like. It gets a driver object pointer, which is created by the kernel, partially initialized and provided to the driver. This is where we're going to continue initializing my stuff. And the second thing here is a pointer to Unicode string structure, classically called registry path, which provides a path to the registry where my driver is installed. This is sometimes useful if I have configuration parameters, stuff like that, that I can read from there. That's fine, but it's not needed for our case. So I'm just going to remove that because otherwise I'll get a warning, and the default compiler settings are treat warnings as errors. So I'm going to get an error and I have to deal with that and all that. So I recommend leaving that option. It's a good thing to have, so we can't ignore warnings. But in certain cases, we're going to do things like that. So if everything goes as expected, I want to return status success here, saying the driver has initialized successfully. Great. So what does the driver need to do? So as we've seen, I'm calling create file on the user mode side. I need to have a symbolic link. I need to have a device, an actual entity that is actually connected to it. So we have to do two things here. The first thing is to create a device object, and the second thing is to create a symbolic link that points that device object in a particular location where create file can actually find it, because create file is limited in what it can do. And the other things we have to do is to say that we support certain operations. So let's get started. So we have driver object here. There's one thing we need to specify is the driver unload, basically saying when the driver is about to be unloaded, we need to do some cleanup. Otherwise, we'll get things that will never be freed until the next restart. So I'm going to call this function unload on unload, and we'll have to write it. This is a necessary thing for every driver. It's like the opposite of driver entry. Where do you do the actual cleanup? Then we need to support a few things. These are the major function codes or dispatch routines. So we know that we need to support device control. We've seen that because the client is going to call it. So we have to support it. So there's IRP MJ device control. That's the index. So I'm going to call that on device control. Of course, we'll have to implement that function. Is that enough? Unfortunately not, but there's one more thing we have to do, because create file itself actually asks the driver of that device, is it okay to give a handle back to the client? So we have to support it. If we don't support it, the default is not allowed, unsupported operation. So we're going to have driver object again, major function. We have two things we have to provide here. One of them is IRP MJ create. This is the what is going to be called for a create request. And we also want to be nice and say that for close, we also want to agree. No reason not to agree. So there's also IRP MJ close. So I'm going to call that on create close. So basically, we're going to do the same thing for both cases. So I'm just going to point them to the same function. In more complex cases, we can do more things in create, like check the color, if it's a color we like, if it has certain privileges and all that kind of stuff. Here, I'm just going to say we agree. So let's implement these things, at least the create and close, which is easy to implement, relatively speaking. So all the dispatch routines, all these array of function pointers have the same prototype, of course, and it looks like this. So we have on create close, they must return empty status, and it accepts two parameters, a device object, which we have yet to create, and an IRP, which is the request itself with the details that we need to look into if it's an interesting request. In the case of create close, there's nothing very interesting here, but still we have to provide the parameters properly. And of course, we have also on-device control, which is actually the heart of the matter. This is really what we're doing, the actual good stuff, the thing we actually want to do. So let's start with create close because it is easy to implement. So let me go here to implement on create close. And basically, we need to say we agree. How do we say that? We need to fill in a status in the iRequest packet in IRP saying this is a success operation, and we can tell the kernel, let's complete it. So here's what that looks like. The IRP has a member called IOStatus, and there's a sub-member called status. We're going to specify success, saying this is good. And there's another member here in IOStatus, if my keyboard decides to work nicely, which is called information, which might provide more information for the particular request. In the case of create close, there's nothing interesting there. So just specify 0, and then we complete the request, which is calling the function IO complete request. If I can type. So we have IO complete request to provide the IRP in question, and there's another parameter which is about increasing the thread's priority, which we don't care about. And we have to return status success. The same status put in the IRP. So this is something that would allow us to actually open a handle successfully to the device, which we have not yet created, and close the handle properly. Basically, the driver is saying, I'm okay with that. Okay, so let's go back to the slides before we continue with the code to kind of pick up a few details. So here's driver entry. Here's what that looks like. It returns a status. If the status is not a successful status, the kernel considers the driver not to be properly initialized, going to unload it, and we're done. Basically, there's some kind of fundamental error, which of course could happen. Maybe we need to allocate some memory or whatever, and maybe we can't do that, and that happens. If we return success, it means the driver has initialized successfully. The registry path is pointing to this location in the Windows registry, HK local machine, system, current control set, services, and a particular name, which we use to install the driver, as we'll do later on once we have a driver to install. And like I said, it's useful in many cases where we have configuration things to read or write. In this case, we have no configuration, so we don't care. Okay, so what do we need to do in driver entry? The first thing is to make sure we have an unload routine. The second thing is to say to the kernel, which operations do we support? Do we support read, write, device control, plug and play? Like I said, there's 28 members, so 28 items in this array. So we're going to support three things. We're going to support create, close, and device control. That's what we're going to support. So we have to specify that in the major function array, which we've already done. The next piece is more interesting and a bit more complex. So in the world of Windows, we have the concept of driver and device. Sometimes people use that interchangeably. The thing device, driver, and in loose language, it might seem fine, but I want to be more precise here because it's very important to understand in order to figure out exactly how things fit together. So a driver is an object that's being created by the kernel. It's represented by the driver object data structure. It's partially initialized and then passed to the driver, passed to me, to further initialize, like we've started to do. And so we're not creating driver objects directly, we're creating device objects. Device objects are the ones that actually are something we can communicate with. So device objects have names, they can have symbolic links. When we call create file, it's about getting to a device, not a driver. There's no direct way to open a handle to a driver, at least not from user mode. There's no meaning to that. Here's a simple example in a way to understand that. Let's say I have two USB cameras connected to my device. The same camera, same brand of camera. How many drivers I'm going to have for that camera? The answer is 1, because it defines the behavior. What does it mean to be that USB camera? What are all the functions there? It's a code. How many device objects I'm going to get? 2. And I have to create them manually. It's not automatic. We have to create them manually. In the world of plug and play, it's going to, plug and play manager is going to tell you, hey, here's a device that I recognize belongs to you. Please create a device object in software to represent it. But here we don't have a hardware device. We're going to create a device manually without any notification from any plug and play manager. But generally speaking, you can see right here, the device objects are really just in a linked list from the driver object. And when you do debugging and stuff like that, we can see all these things, which is beyond what we can cover here. So if we want to have an endpoint for communication, we need a device. Driver is not enough. Driver is just behavior behind the scenes. We need an actual device. So to do that, we have this function. There's a double slider called IOCreateDevice. That's the function that creates a device. We have to call it when appropriate. In this case, in driver entry directly, we want to create a device object and then a symbolic link to it. So this function looks like a mighty function, but it's not too bad. So let's go ahead and create it and use it. So we have here this setup. We didn't implement unload just yet. We'll get to that because right now there's nothing really to do. Now let's call IOCreateDevice. I'm going to do status because these things potentially could fail. So we have IOCreateDevice. What does the function want? The first thing is the driver that this device should belong to. That's easy. We have that parameter for driver entry. We just pass it along. The next parameter is called the device extension size. Basically, the idea is that I can ask the kernel to allocate extra bytes to save state on that per device. This is useful when you have multiple devices, stuff like that. If you don't, then either you don't have any state, like in this driver, there's no state to manage, or you can just use global variables because there's just the one device. So I say 0, please tell the kernel, thanks, but no thanks. Then we have a device name. A device name is needed here because we want to create a symbolic link to it. So we have to do some preliminary work. Let's call that dev name. It has to be a Unicode string. We can initialize that. This is one way of doing that using RTL into Unicode string, which basically what it does, it takes a null terminated string and then just calculate the appropriate size in bytes, just does something like WCS len, things like that, and fills out the data there. It's not allocating anything, it just describes a string. So the way to think about Unicode string, it's not the actual string, it's describing a string, which could be anywhere. So that's one thing. So we have a dev name, we can pass it here. Okay, next. Now we have something called a device type. So device type is relevant for certain kinds of devices like keyboards, mice, things like that the kernel really knows something about. In our case, we don't care and the kernel doesn't care either. We're going to use the file device unknown. Basically telling the kernel, you know what, it's something custom. You don't know anything special about that. It's not special. Just ignore any specialities you might want to have. Then there's another parameter called characteristics, which is a bunch of flags. We don't need them here. And then there's something called exclusive, whether the device can only be opened by a single client at a time. No reason to make that like a case. I mean, I'm open to have many clients talking to a device at the same time. So false means non-exclusive. Any number of handles can be opened at the same time. I'm good with that. And the final parameter, which you just can't see because it's way beyond the slide because of the zoom, it's actually the result. So the kernel is the one that's making the allocation here and returns the result to me. So it's a pointer to a device object that I have here. All this P thing is just a type there for a pointer. And I have here a pointer to a pointer. So I'm passing the address of the pointer. It's going to be filled in with the address where the memory is allocated in kernel space. That's how the function works. Like it or not, that's what we have. So if that fails for whatever reason, it could be that my parameters are bad or something like that, or some other problem like out of memory, then there's nothing really I can do. I'm going to save time, just going to return the status, whatever that status is, and tell the kernel, you know what, there's a failure, sorry, we can't continue. I could add some trace here, dbgprint, to show that in some tools I can capture stuff, but I'm not sure we have the time. So the next thing to do is to create a symbolic link. And that's because the create file function has no access to this device directory. You might be wondering, what is that device directory anyway? So you can see that in tools like WinOBJ from sysinternals, where you have this device directory, and this is how the anti-kernel really looks at devices. It's a tree which is in memory. It has nothing to do with the file system, and certain directories have certain, I would say, roles. So the device directory is a typical one when you put the device objects there, but the things that you want to be exposed to user mode, you have to put in this global 2 question marks directory. This is where you see things like D:, and C:, which are really just symbolic links, shortcuts to something else, to the actual device object. So we need to provide this symbolic link. What you see here is that all these values are valid for the create file function. So we need something like this. And for that, we need to have another call to a function IOCreate symbolic link, which is very kind of simple to use. It says, give me the symbolic link, give me the device name to connect to, and I'll just do that. So we need to initialize one of these things as well. This is the thing that has to match exactly what we see in user mode. So we have here sim name, and sim name can be anything under 2 question marks. That's the 2 question marks directory in the object manager namespace. The name doesn't have to be exactly process power, can be whatever you want, but it makes sense to make them the same, just for easier references for me. But this process power must be exactly like process power here. It must be, there's no way, otherwise they will not connect, it won't work. So we have to match these things. The name could be anything, but it must be the same. So just like before, this is a call that might fail. It might fail if, for example, the symbolic link already exists. In this case, I have to clean up after myself by calling IODelete device. Otherwise, I'll have a memory leak on my hands and I will have to restart the system for this to work. That's all I need for my driver entry function. There are more elegant ways of doing that, but it's good enough for our purposes. The purpose of the unload routine is to do exactly the opposite. So it accepts a driver object, and its purpose is to just do the opposite of driver entry, which means in this case to destroy the device object and the symbolic link. Since I'm not sure we're going to have time to implement that, it's not very complex and not that interesting, I'm going to just implement that as an empty function and that's it. So if we do that, I will have to restart my virtual machine if something goes wrong because I'm going to leak memory. So anyway, we have that in hand. What else? So we have a device object. We have a symbolic link. And now they can connect. So what do we have now? What do we have left to do? The main thing really is to implement the on-device control function. This is where the client says, here's a process ID for you. Please give me a good handle. I can access this process ID from wherever without any limitations of security because you are the kernel. You can get a handle with any power. That's really what I want. So for that, we need to deal with the IRP, the IR request packet. Here's a quick overview of what we have in the IRP. The IRP is really a structure used by the kernel everywhere to represent any kind of IO operation. Whether that's read, write, create, device control, plug and play, it's always the same structure, just different details within the structure. That's what the structure looks like. What we've seen right now is we dealt with status and information to complete the request. But there's some other stuff here, like the system buffer here, which we're going to use, which is going to be a copy of the user's buffer. The user's buffer is going to get a copy to us in kernel memory. We can use that and then also return result in the same buffer. This is what we're going to do. Another thing that is even more important is that there's this IO stack location thingy. So every IRP has a bunch of IO stack locations you can think of like extra information for that IRP. Why do we have several? The number of IO stack locations depends on the number of devices in a device node or device stack. Because you could have filters, for example. For our case, there will be just one, but in a general case, could be more than one. The device I control, the IO stack location actually is more interesting than the IRP itself, because this is where the real parameters are. This is what the IO stack location looks like. There's a gigantic union there called parameters that has a bunch of substructures, all part of that union, meaning they're the same location in memory. But only one of them is valid based on the current request kind. So if it's a read, I have to look at read. If it's a write, there's write. If it's a device I control, there's a device I control. If it's a power management, there's a power. So I have to look at the correct one, otherwise I'll just get junk stuff. So that's what we need to do. Let's go ahead and do that. So I have this on-device control function. This is what we need to implement. That's the crux of this driver. So let's see what that is going to look like. So first thing, we need to get the information, and the information that is interesting is in the IO stack location. So let's call that IRPSP. There's a function called IOGET current IRP stack location that basically takes the IRP pointer and just points to the IO stack location for my layer. I don't know what my layer is. Maybe there's a filter on top of this device, of my device. I don't need to care. I just ask, give me my stuff. And within that IRP, IO stack location, there's the stuff that I care about. This is the device I control thing. So if I go to my IRPSP and I look at parameters, and there's a device I control here. That's the substructure in the parameters monstrous union that I need to look at. So I'm just taking a reference to that, or if you care about, if you prefer pointers, go with pointers, doesn't matter. And what do I have here? So the first thing that I have is the IO control code. This is where the IO control code comes in, the one we used in user mode. We provided some IO control code. So the driver has to define it. And so I have to add a file here to the driver project, a header file. Let's call that process power common, where the common means that it is common to user mode and kernel mode. This is we're going to define ioctl open process. Now you might think it's very easy, just give it some random number. I mean, what's the big deal? Unfortunately, this is not how it works. In fact, the way you define this constant is based on another macro called control code, which says more things about how buffers are passed in to the request. I'm not going to go over that, but the point here is that you just can't take some random number like 17 because you like 17 and just put it here. You can't. And so there are four parameters to this macro. The first one is called the device ID, which can be anything you want that is at least 8,000. That's what Microsoft says for custom device names, fine. And then you have a function number, which could be 800 and up. So if you have multiple control codes, at least this number can be incremented, so they won't have the same value. And again, the documentation says, please use 800 so you don't collide potentially with Microsoft provided numbers. And then we have something called the method, and this is where really we specify how buffers provided by the client. Remember, there are two buffers, input, output, how they're passed to the driver. There are several options, 4 options in fact, but we don't have time to cover that. But if I use method buffered, it's going to pass me this buffered in that system buffer member. That's all that's important here. So once I have that, I'm going to go back to my driver. I'm going to include that so I can use that. So we have process power common. I also have to include that in my client application because now I can finally compile the client. So I have process, actually I have to go back, process power and process power common. So now if I look at my create file and device I control thing, now this is supposed to work unless I misspelled something, which is definitely a possibility. So let's see, ioctl open process, I misspelled things. Like little switch there. So now we have that at least the client is compiling fine. At least the client is compiling fine, but of course the driver is not done yet. So now when we look at the control code, we say, okay, if this is ioctl open process, we can talk. If it's something else, I have no idea what that is. And again, I can include other control codes in the future. So what do we do now? Now we have a pointer to the buffer. The buffer, if we look at the process ID that we actually need, the buffer itself is in IRP, associate IRP, this is a union, system buffer. This is just the pointer where the user data is stored. That's the process ID. I actually have to check the size of the buffer because if it's too small, I might crash the system. I'm not going to do that to save time. So this is the pointer to the buffer. I'm just going to dereference that. and take that as a ulong, if I can type properly with this bad keyboard, and get that process ID. So I'm going to assume here, for the sake of time, that I have something that is at least 4 bytes in size. I can grab these 4 bytes in size. So once I have this process ID, I want to open a handle to it. Now in user mode, I will do open process as we did, but here I'm going to call ZW open process. This is the sort of kernel equivalent, if you will, but with the power of the kernel, where I can open a handle to the process with any access that I want. So let's go ahead and do that. So first we have the result. That's the first parameter. It's kind of weird, but this is how many kernel APIs work. So we have the H process as the first parameter, not as some kind of result at the end or something. Then we have the access. So I can say process all access. The simplest things to do. Just say, you know what? Give me everything. I want to do with the process whatever I want. Not just a particular thing that that particular client wants. And then we have 2 parameters we have to provide, an object attributes thingy and a client ID. So what is that all about? So first, the client ID, which is more understandable. I mean, what we're missing here is the process ID. Where do I provide it? It's provided as part of this client ID thing, which actually is just a small structure that has 2 members. One of them is unique process, and the other one is unique thread. So it can be used with opening a thread as well. So I have to put something in unique process. And this is where I need to provide the PID. Well, very close to that. In fact, unique process has a type called handle, which might make you think that this is in fact a handle. It is not. It's an ID. And the reason it's typed as handle is because the way the kernel generates process IDs is using a private handle table. That's a kind of a different thing. So anyway, what I want to do here is just to do the proper casting. In order for me to do that in a more elegant way, there's a function / macro for that called ulong to handle does that for me. Basically extends that 4 bytes to 8 bytes. That's it. It's not really, I can do this thing manually, and you can also press F12 and see the actual definition. So that's giving me the client ID. The other thing that remains is this structure called object attributes, which is a common structure that appears in every kind of open function you'll find in a kernel, or a create function. It provides extra details. In this case, very few details are actually needed, but unfortunately, I do have to initialize that. So if you look at WOpen process, you can see that object attributes is an in parameter. There's no OPT there, which means it's not optional. I have to initialize that, but it's not very difficult to do. One way of doing that is to use RTL const object attributes. Technically, I can specify some name here, which makes no sense for a process, and some flags, which we don't need. In fact, 0 is the right thing to do here. That should be good enough. Let's go ahead and pass that attribute here, like so, and we should be fine. So now that we have that, of course, this could fail. So we have the status here. Let's go ahead and do some preparation. Let's start with the bad status, like invalid device request, which is a common status to say this is a control code I don't really know. So let's just do that. And then let's see, why is this macro not happy? Name, and looks fine to me. Okay, we'll see. So that's one thing. So if this fails, I can check it with this macro. Let's just break. And when we get out of the switch, we're going to complete the request with whatever status we have so far, which in this case is going to be some bad status. For example, maybe the process ID is garbage, so there's no way to do that anyway. If it's okay, we can take that handle, which is now valid, and I want to copy it back to the user's buffer. That's the same buffer that's going to be then copied back to the actual user buffer after I complete the request. So I can do something like this. This is one way of doing that. I can take IRP, associate IRP.system buffer, the same pointer really, and just stuff into it H process. If you want to do a mem copy or whatever, it's the same thing really, just stuff it there. And the important part here is that I have to say that the request really has an output which is the size of handle. So when we complete the request, we'll see that there's a length parameter there, and we have to provide the correct value, otherwise the data is not going to be copied back to user space. Once we have that, we just need to complete the request. So I'm going to go here, copy the the code to complete the request, same code basically, but make the appropriate changes. The status is whatever status we had, and the length is where the information field here in this case has a meaning, where it's the number of bytes that I would like to copy back to the user's buffer. So I have to specify something like len here in the case of success. And that should be basically it. So the last thing that we can see the compiler is happy, even though the squiggly is there. The compiler is happy, but there's a linker error saying that it doesn't find some driver entry thing, and the only little thing here is that driver entry has to be an extern C. It has to be a C-linked function, linkable function, and since the CPP file, the compiler expects that to be a C++ function. So now the linker is going to be happy, and we have a driver. Whether it works or not, that's a completely different story. So let's test this thing. Okay, so we have here the output. So I have a new list DLLs, of course, which has the idea of looking at the driver and the actual driver. I'm going to copy them, go to my virtual machine, and now we're going to paste them here. I'm going to override the list display. So we have the driver here, that's nice, but it's not installed yet. We have to install it, and that requires administrative access. So let's install that. So in order to install that, I'm going to install that just like you install services. If you ever installed services in Windows, using command line like etc is the same thing. So let's call that process power. That's going to be the registry key value, which doesn't really matter, the key name. Type equals, I'm sorry if it's a bit small. Kernel, it's also in the slides. And the bin path equals ctest. And that was process power.sys. So it says success. It means it was installed successfully, just that. It hasn't been loaded yet. Let's now load it using SC again with start, process power. That's just the name of the registry key name. So we didn't get a blue screen, which is one good thing, right? And now we can test it. So we can test it by going back to a command window just before, like before. Notice it is a command window without even admin access. So let's cross fingers. I mean, the demagogue's not always nice, but let's try. And it works. So we now see the DLLs inside CSRSS, all the modules loaded into the CSRSS process. And we're doing that using the driver. Without the driver, it just won't work. It just can't work. So there you have it. And we have even 2 minutes to spare. So I think that was like a big deal. I'm happy to take questions. If you want to ask questions later, that's also fine. And if you're completely like overwhelmed and have no questions in mind, like what the hell was that, that's also fine. I mean, that was part of that. So thank you. Yes? Going back
to the when you were at the window VJ, it was called, there was the question mark
yes.
folder, okay? And I saw a con and a null in there, which I know you can access any directory. Is it the same for any other driver object? Or is it...
Yes, it's the same. It's another symbolic clean. So you can use the create file with //dot/null or con and access that thing. Exactly in the same way. And by the way, I didn't show you that, but all the other details that I talked about are just here. So you can see here how to install a driver. That's installation driver without an INF file. This works for simple kinds of drivers like this one, which only has software components. So install that in this way. And if you have a more complex driver, like dealing with hardware, you do have to use an INF file. If you're familiar with tools like Process Explorer from sysinternals, it's doing exactly the same thing behind the covers. Really, the create service API is the one doing the heavy lifting. So if you run Process Explorer as admin, it installs a driver. And by the way, you'll see that if you look at the DLLs in Process Explorer, when it's running with admin, you'll see all the DLLs even for protected processes. Why? It's doing exactly what I did here. In fact, I did that for Process Explorer back in the day, a few years back. In version 17 and forward, you can do that. If you have version 16, you can try that. You'll see CSRSS you won't see any DLLs because the Process Explorer uses the normal open process function. If it fails, it just fails. So everything is here if you want to look at that later on. One thing I didn't mention is that the virtual machine was configured for test signing mode. Otherwise, you can't load unsigned drivers on a normal Windows system. This is one of the basic things that was added in Vista for 64-bit systems. So the fact that I could load the driver, you can install the driver in any system, but loading, that's a different thing. So loading won't work if you don't have test signing on, and this is the way to specify that. You have to do that once, restart the system, and then you're in test signing mode. You can see on the bottom right, it says test mode, and that's what that means. So I did that, of course, beforehand, and that's why it worked. Yeah?
You frequently were using the wide Unicode. Are those ever going to change to a UTF-8?
No. The kernel works with UTF-16. It's not going to change. UTF-8 is problematic because every character has a different potential length. So random access is problematic, and the kernel really can't be re-architected to work with that. Any other questions? No. Thank you.